addition, multiplication, function composition, modular addition, matrix multiplication, group laws, logical and, logical or, concatenation, and even the greatest common divisor are all associative operations. Is there anything linking these operations together? The answer is surprising and has profound implications. By the end of this video, you will understand that associativity is not merely a property, but an idea. You've probably first learned of the associative property in elementary school. Whenever you've learned it, you were likely told that associativity is a rule, written like this for addition and like this for multiplication, that you should learn associativity in order to do arithmetic computations like this one, or this one. That associativity means the order of operations does not matter, and as such, where the parentheses go does not matter. It was probably taught alongside commutativity, and you might even remember which is which. If this sounds like you, I want you to know that your ideas about the associative property have been corrupted. But don't worry, it's not your fault, nor is it your teacher's fault. The fact is, your teacher didn't know any better. When is the last time you used the associative property to get through an arithmetic computation? Think about how you would solve this equation. You probably use a much more clever trick to navigate arithmetic, what I'll call the jumbling property, which is true of operations that are both associative and commutative. This is the property that allows you to ignore parentheses and combine numbers in any order. I think on some level, we realize that this is more useful for arithmetic and mostly ignore the associative property until we meet our first non-commutative operation, like function composition or matrix multiplication. By then, it's too late. A curiosity about the associative property is all but gone, which is a shame because I think it is the most powerful property of operations, and once you understand it, I think you will agree. An eye-opening challenge is to try to explain to someone what an associative operation is without simply describing the formal property in words. To make the challenge more concrete, avoid reading the equation, and try to avoid using the words parentheses, order, group, and their synonyms. If you think you have an answer to this challenge, I would love to hear from you. Please, comment it below. So now we know how associativity is typically explained and what its definition is. But what, if anything, does associativity tell us about operations? To find out, let's start by looking at a handful of associative operations, starting with addition. Suppose in one bowl I have 2 apples, and in another bowl I have 3 apples. I would like to combine the apples from the 2 bowls. If I do so, and then count the number of apples, I would find that I have 5 apples. Mathematically, this observation is written as 2 plus 3 equals 5. And it means 2 things and another 3 things makes 5 things. In this case, the numbers stand in for objects, like apples in a bowl. Now consider starting with 2 apples in a bowl, and then dropping 3 more apples into that bowl, and ending with 5 apples in the bowl. The same mathematical expression is used to express this scenario, 2 plus 3 equals 5, but the meaning has changed. The 2 and 5 represent states of having 2 or 5 apples, but the 3 represents the action of adding 3 more apples. To emphasize that 3 represents an action, we will give the 3 a glow. Now the equation means starting with 2 things and adding 3 more makes 5 things. Now consider one more scenario. Into a bowl that is partially filled with apples, drop 2 apples, and then into the same bowl, drop 3 apples. This is equivalent to dropping 5 apples into the original bowl. Again, the mathematical expression is 2 plus 3 equals 5. But the meaning is adding 2 and then adding 3 is the same as adding 5. Now all the numbers represent actions, the action of adding more apples. So we have 3 ways to interpret the same equation. The first interpretation describes a relationship between objects. The second describes the change in an object due to an action. And the third describes a relationship between actions. This ability to use the same mathematical expression to describe objects and actions is going to be central in investigating associativity. To give it a name, I would call it object-action duality. We can find similar object-action dualities existing in other associative operations. Let's look at multiplication. In a drawing with 2 parallel lines and another 3 parallel lines, the number of intersections is 6. If we place apples on each intersection, we form an array of apples. We can break our array into number of rows, number of columns, and number of objects. The relationship between the 3 quantities is expressed mathematically as 2 times 3 equals 6. This is the object interpretation of multiplication, where each of the numbers represents an object. Now consider the scenario where you start with 2 apples, then put the apples through a copying machine, which replaces each apple with 3 copies. The final result will be 6 apples. The same mathematical formula expresses this observation: 2 times 3 equals 6. This is the object-action interpretation, where 2 represents the starting state, 3 an action, and 6 the end state. Now consider what would happen if you produce 2 copies of everything, and then produce 3 copies of everything. This will be equivalent to just producing 6 copies of everything. As a formula, we find the same equation: 2 times 3 equals 6. But the numbers now all represent copying actions. Addition and multiplication are familiar operations that are both associative and commutative. Let's look at a less familiar operation that is associative but is not commutative. See if you can guess how it works based on these examples. The name of this operation is concatenation, and it is performed by linking the inputs together in a sequence. Let's show that it is associative by evaluating this expression. First, we will concatenate what is in the parentheses. X concatenated with y is xy. Then we will concatenate xy to z. The result is xyz. xyz is the same as x concatenated with yz, and yz is the same as y concatenated with z. And we find that concatenation is associative. Now let's show that it is not commutative. X concatenated with y is xy, but y concatenated with x is yx. These are not equal in much the same way that no and on are not equal. And we find that concatenation is not commutative. Something pretty cool about concatenation is that its existence is implied between adjacent characters in text. That is, concatenation is built into the foundations of writing. It is what glues letters to each other, and this gluing is associative. The object-action duality also exists in concatenation. Consider having a tile with a 2 and a tile with a 3. If we concatenate these tiles together by gluing them, we produce the sequence 23. The equation which describes the scenario is 2 concatenated with 3 equals 23. This is the object-object interpretation, where the inputs are sequences of tiles, or, if you're familiar with programming, strings of characters. To get the object-action interpretation, start with the character 2 on an otherwise blank scroll. Write the character 3 to its right. The result is a scroll with the sequence 23. The equation which describes this scenario is 2 concatenated with 3 equals 23. Now consider writing a 2 followed by writing a 3. This is equivalent to writing 23. The equation describing this scenario is 2 concatenated with 3 equals 23. This is the action-action interpretation where the numbers represent actions. We've looked at 3 examples of associative operations and how the object-action duality applies. Now I would like to look at one more example of object-action duality: function composition. But before we investigate function composition, let's break down what a function is. Most of you will recognize functions as being defined by an equation. But a more powerful and intuitive way to think about functions is as a machine that takes in an object, transforms it in a well-defined way, then outputs the result. The function need not be an equation. It can be a set of instructions, a graph, a piece of code, a process, or a mapping connecting inputs to outputs. The input and output objects need not be numbers. They can be anything that is well-defined. With a better understanding of functions, let's explore function composition. Function composition takes 2 functions as inputs and links them together by feeding the output of the second function as the input of the first function. What we've done with function composition is create a new function, which passes the input through f and then through g in an assembly line fashion. The order of the functions in the assembly line matters. Watch what happens when we swap f and g. In the first instance, f, which outputs the color red of the input, feeds its output to g, which then outputs the color word red. In the second instance, g outputs the color word red in a white font, and f extracts the color. Although they started with the same input, their outputs are different, making the 2 functions different. And this demonstrates that function composition is not commutative. Although not commutative, function composition is associative. To illustrate, let's construct this function, where f, g, and h are arbitrary functions. The expression tells us to first link g and f together, then link h to the result. We have ended up with an assembly line connecting f to g to h. Now, let's change the parentheses and construct this function. The expression tells us to first link h and g together, and then link f to the result. The constructed functions are the same, regardless of how we associate the starting functions, and function composition is associative. See if you can construct the different interpretations for function composition on your own. What would be an object-object interpretation of g composed with f equals h? What would be an object-action interpretation? And what would be an action-action interpretation? If it helps, you can make the problem more concrete by defining f as the square function, g as the square root function, and h as the absolute value function. There is no one right or wrong answer here. Trying to construct these scenarios for yourself makes a much more powerful impression than me supplying you with scenarios. I left my own scenarios in the video description for those who want to take a look. If you have one you would like to share, please do so in the comments. I would love to see it. Our exploration of associative operations seems to suggest a pattern. So far, we've looked at a handful of associative operations and observed that they can always be interpreted as acting on objects or actions. This pattern turns out to be much more general than associative operations. In fact, object-action duality exists for any operation and deserves a video on its own to do it justice. If you're interested in having me make a video on it, stick around for the end of the video poll, where you can vote to make it the subject of the next video. What we will see, however, is that this duality creates two interpretations for associativity that are equally powerful. Now, I want to shift gears a bit and show you an operation on actions that is closely linked to the associative property. This is the and-then operation, and I will write it using an ampersand character, although as far as I'm aware, this is not a standard notation. This is the same and-then that is used when telling a story, such as Jack went up the hill and then Jack fell down. Consider this three-step procedure for getting milk from the fridge. 1. Open the fridge. 2. Look for the milk. 3. Take out the milk. We can connect the first two steps into one action using and then. If we open the fridge and then look for the milk, we'll say that it's the same as searching the fridge for milk. Now the procedure is search the fridge for milk, take out the milk. Let's combine these two actions using and then. If we search the fridge for milk and then take out the milk, we'll say that it's the same as getting the milk. Starting with the original procedure, we can choose instead to connect the last two steps into one action. Looking for milk and then taking out the milk, we'll say that is the same as retrieving the milk. Now the procedure is open the fridge, retrieve the milk. Let's combine the actions together using and then again. If we open the fridge and then retrieve the milk, that is the same as getting the milk. Recalling our previous result, we find that no matter in which order we apply the and then operation, it gives us the same action. Thus, the and then operation is associative. This gives us another clue as to the possible meaning of associativity. I've shown you many examples of associative operations that describe actions. The most recent example hints at the special relationship between associative operations and the and then operation. What I wish to convince you of is that this relationship is much deeper than you might suppose. In fact, associative operations are precisely those operations that mean and then. To convince you that this is the case, we will first have to formalize what is meant by an action and what is meant by an and then operation. We'll start with actions. Actions transform an object. During an action, the state of an object is changed from its initial state to its final state. By black boxing, an action can be thought of as a function that maps initial states into final states. Calling the initial state S, we will denote the final state as A. When read from left to right, it reads start at state S and then apply action A. So now we understand that, mathematically, actions are functions which map start states to end states. In light of this, we are ready to investigate the mathematical description of an and then operation. An and then operation is an operation that takes two actions and combines them into a procedure. The resulting procedure is an action. Do B and then do C. Let's formalize this idea by applying the two-step procedure to a starting state S, which is the same thing as starting with S, applying the action B, and then applying the action C. This is the defining property of and then operation. It is a formal expression of what it means to be and then. We have not yet defined what placing two actions side by side like this means. Note that this is not the same as placing a state side by side with an action, which we defined earlier. This frees us up to define BC however we like. Here, we will define BC as B and C. This definition is purely for notational convenience, readability, and elegance. It is not necessary for continuing our investigation, but I found that the flood of ampersands are distracting enough to warrant a notation change. Going back to the and then property and applying our new notation, we find something that is tantalizingly close to an associative operation. But in their current form, they are not the same. The problem is that BC is the and then operation, while SB is the apply action operation. This is different from associativity, where the two operations are the same. However, we can show that the and then property implies associativity. This would mean that all and then operations are associative. This shouldn't be too surprising. In fact, we've shown it to be the case once before. Only this time, we would like to prove that this is true of all actions, not just when getting milk from the fridge. How can you be sure that this will always be true? How do you know there isn't some combination of actions waiting to be dreamed up which does not associate under and then? How would you prove that all and then operations are associative? A good starting place might be the defining properties of and then and associativity. If you're up to the task, I encourage you to pause and see if, starting with the and then property, you can derive the associative property. I won't go over the proof in detail, but I will provide a quick animated proof. If you would prefer not to spoil the problem, you can skip the animated proof by going to this timestamp. For everyone else, the proof is as follows. Please feel free to pause and ponder some of the steps in the proof. Take S to be any starting state. And finally, since the two actions change every possible starting state into the same end state, the two actions are equivalent. So now we see that the and then property implies associativity, meaning that all and then operations are associative. As we've noted before, this isn't too surprising. The real surprise is that the reverse is true as well. That all associative operations are and then operations. To prove this, start with an associative operation star. Now, for each object X, define a corresponding action X as the act of operating on the input state with X. That is, starting with S and applying the action X is done by starting with S and then operating with X. To get a feel for the meaning of this statement, think about how it relates to our previous examples. In addition, the action X is the act of adding X to the starting state S. In multiplication, the action X is the act of multiplying the starting state S by X. In concatenation, the action X is the act of concatenating X to a starting text S. In function composition, recall your interpretation of the object-action equation, or, if you didn't before, try to think up an interpretation now. Note that your action meant function compose with f, which is in line with our definition of actions. You should now get the sense that this definition for the action x is really a direct way to use an operation to generate an action interpretation. Now, let's apply our definition to rewrite the associative property in the language of actions. A star B becomes start with A and then apply B. AB star C becomes start with state AB and apply C. On the left-hand side of the equation, A star B star C becomes start with A and apply the action B star C. Finally, compare this last line to the and then property. It's the same, only now A stands for the state instead of S, and the star operation obeys the defining property of and then operations. So, starting with associativity, we successfully constructed an interpretation in which the associative operation is an and then operation. We also showed that the reverse is true. In other words, we showed that associativity of an operation implies it is an and then operation, and that being an and then operation implies associativity. When two statements imply each other, they are logically equivalent. Thus, associativity means that the operation is an and-then operation. We are now ready to see associativity for what it really is. Associative operations are and-then operations. And, like in Jack and Jill, they each tell a story. Let's briefly explore the and-then representation in each of our examples. Addition is add 2 and then add 3. Multiplication is make 2 copies and then make 3. Concatenation is write 2 and then write 3. Hopefully by now you see the same beauty that I do in the associative property, but the interpretation of associativity is not only beautiful, but as I hope to show, it is valuable. I would like to show how it can take an impenetrable subject and reveal its hidden meaning. Let's pursue the subject of groups. Groups are what kickstarted this journey for me. The more I studied groups, the more empty, joyless, and opaque the subject felt. I finally narrowed down my problem. I didn't understand associativity. Well, now that you have what I was lacking, I can properly introduce you to this deep subject. Start with an equilateral triangle and find all 2D isometries, that is, rotations, reflections, translations, which do not change the image of the equilateral triangle. We can rotate by 120 degrees. We can rotate by 240 degrees. We can rotate by 360 degrees, which is the same as rotating by 0 degrees, or just doing nothing. In group lingo, the do-nothing action is called the identity. We can also reflect horizontally. We can reflect along the 60-degree line. And we can reflect along the minus 60-degree line. Now we introduce the group operation, which takes 2 actions as input and performs them back to back. For example, a 120-degree rotation followed by a 240-degree rotation would be equivalent to a 360-degree rotation, which is our do-nothing action. Since each individual action preserves the equilateral triangle, the resulting action is guaranteed to also preserve the triangle. We can form a sort of multiplication table using all the actions, and, with some patience, fill it in one by one. This would fully define the group operation. Now we have a simple example of a group. Can you tell whether or not the group operation is associative? We could do it by exhausting all 216 possibilities for inputs, but if we use our newfound understanding, it's now almost trivial to prove it. If we show that it is an then operation, then we know it is associative. The answer was baked into our construction when we defined the group operation as an and-thenning of symmetry operations. Since it's an and-then operation, the group operation is associative. Most students are introduced to groups through their definition as a set G with a closed operation, which is associative, has an identity in G, and has inverses for all elements. Some examples are usually supplied, but the meaning of these properties is rarely explored. What are we really studying when we study groups? Let's break down their meaning using what we've learned. In place of associativity, let's write and then. Better yet, let's just replace the group operation with the and then operation so that and then is left implied. Since we are using and then, we should interpret the elements in the group as actions. The identity states that there exists the trivial do-nothing action in the group, where the end state is simply the start state. So we can replace identity with its meaning, can do nothing. The inverse property states that every action can be reversed. This means that actions can be undone. Taken together, groups study the and-thenning of undoable actions. In plain English, groups study reversible procedures. This includes anything from addition and multiplication to symmetry transformations, Rubik's cubes, rotations, and physics, where at the graduate level, it's hard to avoid learning about groups. The thing that connects all these subjects together is that they all describe reversible procedures. So now you can see why mathematicians get excited about groups. I find that the and-then interpretation of associativity has been the most valuable and illuminating for me, but there is one more interpretation that is arguably more elegant. This is the idea that associative operations always define a gluing together of two objects, which I will label with the concatenation operation because it is the operation that is closest to gluing. To see where this interpretation comes from, start with the and-then interpretation of an associative operation. Now, using object-action duality, let's think about what it would mean to perform the and-then operation on two objects. I want to show a general way to turn any action into an object. Start with a timeline. Each action can be represented by the space occupied by that action on the timeline. Let's say the red region represents the action of opening the fridge, the green region looking for milk, and the blue taking out the milk. Another way to think about these actions is as film reels, whose first frame is the starting state of the action and whose last frame is the end state. When operating on actions, and then operations combine actions together to make a new action sequence. But the and then operation can also be viewed as a temporal gluing of events, or as the splicing together of the film, such that the first frame is the starting state of the first action, and the last frame is the end state of the last action. We now see that the dual of and thenning is gluing. An and then operation is a gluing of actions, and gluing is an and thenning of objects. The two are object-action duals of each other, and then is applied to actions, and gluing is applied to objects. Let's go back and see how gluing occurs in the object-object interpretations of our associative operations. In addition, we glued together the apples in the bowls to construct the total apple count. In multiplication, we glued together the rows and columns to form the array. In concatenation, we glued the tiles to form a new sequence. With our newfound understanding, we can now see how your ideas about associativity have been corrupted. You were told that associativity is a rule. While this is the defining rule of associativity, it obscures the meaning of associativity. It would be as if teachers everywhere explained that this is temperature and left it at that, never elucidating that temperature is a measure of heat. Later on, when encountering heat flow in a steam engine, would those students think to recall this equation? Similarly, when encountering sequences of actions, would a student reach for associativity? Did you reach for an associative operation when you tried to solve a Rubik's Cube? Perhaps next time you will. It amazes me how a mundane concept like associativity can reveal such dazzling insights with the right probing, that its meaning can remain hidden even after centuries of instruction. I think that, at least in part, the concepts of and then and gluing are so commonplace that we fail to recognize their structure, much in the same way that a fish might fail to recognize that water takes the shape of its container. Thank you for joining me on this amazing journey into the depths of the associative property. If you enjoyed this video and want to see more like it, you can let YouTube know. Like, comment, subscribe, and hit the bell icon to be notified when I make a new video. You can choose my next topic. Follow the link in the description to vote for what you think my next video should be. Finally, I would like to give a heartfelt thank you to 3 Blue 1 Brown for starting the Summer of Math Exposition contest. I probably would never have started this channel without that extra push. If you stuck around this long, you are probably already subscribed to 3 Blue 1 Brown. If not, I suggest you check out his channel. He is one of the best math YouTubers around.